all, I'd like to thank organizers for the invitation and provided opportunity to present here my research results. I'd like to discuss the problems associated with the theory of multidimensional nonlinear wave structures of the soliton type in dispersive complex media and some applications in real physical media. So, after some introductory remarks, we'll write basic equations and consider the classes of nonlinear generalized cartons of Petriashvili and derivative nonlinear Schrödinger models. And after that, we consider some applications of these models in a plasma and other dispersive media. The solitons as nonlinear fundamental structures of the waveguide are interesting as the investigation plays an important role both at study of general wave dynamics and at simulation of nonlinear wave processes in a plasma, and also at study of propagation of wave structures in the atmosphere, ionosphere, magnetosphere, and hydrosphere of the Earth and other planets. Generalization of the basic equations, which will be considered in my talk, concern first of all to various complex physical media, where it's necessary to take into account the high-order dispersive corrections, influence of dissipation, of viscous type and Landau dissipation, instability and stochastic fluctuations of the wave fields. We also discuss here the wide spectrum of possible applications of the theory. We start from a full set of hydrodynamical equations written in the generalized form. These are the equation of continuity, equation of motion, equation of continuity, and equation of motion for potential, and Laplace equation. Here you can see the boundary conditions in the terminology of wave on the water, on surface of water. This one is equation of surface of water, and this one boundary condition on the water. Independence of on physical sense of functions and variables in this set. This set of equations describes the waves on water surface. In this case, rho has a sense of the water depth. C is the phase velocity of linear waves of small amplitude. Next example, ion acoustic waves in a plasma. In this case, C is ionic velocity. And next example, the fast magnetosonic waves in magnetized plasma. In this case, rho has a sense of dimensionless magnetic field, and C is a Archian velocity. From this set of equations, keeping in the composition the terms describing nonlinear dispersive and dissipative effects with the same accuracy, we have obtained the modified GKP DNLS equation, so-called BK model. This model describes two classes of systems. The GKP class of equations in case when differential operator A takes the following form, and DNLS, derivative nonlinear Schrödinger class of equations, if operator A has the following form. Here U has a sense dimensionless magnetic field, magnetic field of the wave. So, the Wiki model can describe the evolution of three-dimensional alpha and fast magnetosonic waves in magnetized plasma, for example, in magnetosphere and solar corona. At first, let's consider the equations of first class, namely the generalized Kardashev-Petriashvili equation, which is valid always in all media when the dispersion law is following form. Here, for example, for FMS waves, the coefficients are the following. And you can see that dispersion depends on the angle between wave vector and the magnetic field. The term proportional to the second derivative in this equation describes dissipation of viscous type, and if Landau damping is significant, we should also include in right-hand side of equation this term. For waves on shallow water, the coefficients in the GKP equation are the following, and you can see that dispersive coefficients are the functions of depth of the water. You can see the example, tsunami waves on shallow water. To speak about existence of soliton solutions, it's necessary to prove that they can exist in the decay model. Let's write the GKP equation in the Hamiltonian form, with Hamiltonian, which has a sense of energy of the system. Variational problem is formulated in form of variational equation, which has the following sense. All finite solutions are the stationary points of Hamiltonian at fixed moment of projection Px. According to Lyapunov's theorem of stability in dynamical system, the points that correspond to minimum or maximum of Hamiltonian are absolutely stable. Considering the deformations of Hamiltonian concerning moment of projection Px, here T is the spatial dimension, write Hamiltonian of the GKP equation in the following form with integral coefficients A, B, C, and E. Necessary condition of extremum is this set of equations, and sufficient condition of minimum is this set of inequalities. Solving these sets in common, we obtain the following results. The pictures show the changes of Hamiltonian in two-dimensional and three-dimensional geometry for various values of the integral coefficients along these lines. So we have proved a possibility of existence of absolutely and locally stable two-dimensional and three-dimensional soliton solutions, and obtained the conditions of solidal stability independence on dispersive parameters, i.e. the characteristics of media. For the 3D NLS equation written in the Hamiltonian form, we investigated the Hamiltonian boundness in real vector space C by analogy with the case of the GKP equation. Our result, we have proved a possibility of existence of absolutely and locally stable three-dimensional solutions in the 3D NLS model and obtained the conditions of stability of the soliton solutions, i.e. regions or values of the equation coefficients. Possible types of solutions. Quantitative analysis of the GKP dynamical system enables us to classify possible solutions in multidimensional space. For example, for three-dimensional GKP equation, this is a 12-dimensional space. You can see here the phase portraits and solutions for various values of equation coefficients in non-dissipative case without instability, and in case of dissipative equations with dissipation and instability. In the first case, there are the single points of integral curves of types of saddle center and stable focus and unstable focus. That corresponds to the soliton solutions with monotonous and oscillating asymptotic respectively. In the second case, there are the single points of types of saddle here and saddle field focus. That corresponds to the solutions of types of shock waves and the wave packet which disperses with time. The asymptotes of solutions can be exponentially, in this case, and oscillate. As an example, in two-dimensional case of the GKP equation can have stable soliton solutions with monotonous and oscillating asymptotes in dependence on signs of velocity and dispersive parameter p. Interaction of multidimensional solitons with the GKP model, unlike model of classical Kadamtsov-Petriashvili equation, can be essential more various. Figure shows a trivial case when in slanting collision the solitons with algebraic asymptotes exchange the momentums and energies like in the classical PP model, initial time and past time. Next figure shows non-trivial case when one can observe the formation of bound state or outstate or a so-called P soliton of the GKP equation. Influence of dissipation on the soliton structure. The dissipation of viscous type is described by the term being proportional second derivative in the GKP equation. Left picture shows the evolution of two-dimensional soliton with algebraic asymptotics, and right picture shows evolution of two-dimensional soliton with oscillating asymptotics. You can see that in both cases, dissipation in the system on a level with general damping of the wave field amplitude directly influence on the structure of two-dimensional solitons. In all cases, we observe effect of elongation of the soliton tail, decreasing of frequency of oscillations and damping of oscillation height of the main maximum, and asymmetrical changes of integrals, momentum and energy in front and back cavities, where function u is less than 0. Well, now let's consider some applications. First of them is propagation of the fast ultrasonic wave beam in magnetized plasma. If these inequalities are valid, the dispersion relation takes the following form. And in this case, the structure of FMS waves depends on sign of dispersion coefficient beta. So depends on the angle between wave vector and the magnetic field. But near the cone of angles where dispersion changes its sign, where beta tends to 0, structure of FMS waves depends also of sign of the dispersion coefficient gamma. In this case, the GKT equation takes the following form, where H is the dimensionless magnetic field of the wave. In this picture, you can see three regions for different types of dispersion. Region B corresponds to the case of negative dispersion, and regions A and C to the cases of mixed dispersion when the sign of dispersion differs for short and long waves. Let's formulate the problem. There is a three-dimensional stationary plasma-sonic wave beam propagating in plasma at the end of the magnetic field near this cone where dispersion changes its sign. Using the scale transformation, we transit from initial problem to boundary one. The problem has been solved numerically with boundary condition in form of axially symmetric stationary beam and boundary x equals 0. These pictures show the results. You can see that in regions B and C, magnetic sound scattering, these curves, magnetic sound scattering takes place. And in region A, the dynamics of the beam is more complicated and consists from three stages. Subfocusing stage, here, when the beam amplitude grows exponentially with time, you can see it's bigger. Stage of nonlinear saturation, when the dispersion effects of higher order starts to play a predominant role. And after that, we observe the stage of diffusing with formation of stationary plasma-sonic wave in this time. These pictures show the evolution of solution in x-rho plane corresponding the stage of maximum of amplitude of beam. You can see here the flapping of the pulse wings behind the main part of the pulse with formation of the ring structure behind main maximum. Next example is the nonlinear effects for three-dimensional advanced solitons in a plasma. We solved this problem in axially symmetric geometry with two kinds of initial conditions. First, soliton-like axially symmetric pulse, and second, modulated plane wave. These pictures show our numerical results on evolution of initial pulse, three-dimensional left picture, three-dimensional right singularly polarized axially symmetric nonlinear pulse, and right picture evolution of three-dimensional right singularly polarized modulation plane wave for different values of equation coefficients. You can see that in the first case, the initial pulse weakly limited in the transverse rho direction. When the stability condition is satisfied, The evolution results in formation of the stable three-dimensional axisymmetric solution. At opposite signs of equation coefficients, that is equivalent to check these changes, the Hamiltonian of the equation becomes negative, and a three-dimensional affine wave spreads with evolution. This figure shows another case. In the picture, you can see that the condition of existence of the local minimum Hamiltonian is not satisfied, and one can observe the development of the three-dimensional collapsive solutions of the three-dimensional DNLS equation. In case of left secularly polarized modulated plane wave, for three-dimensional nonlinear wave modulated wave pulse for all above mentioned cases, one can observe a mirror opposite picture. Next example is the nonlinear waves in media with variable dispersion. For example, that takes place on starting of the evolution of three-dimensional FMS waves in magnetized plasma, when in the GKP equation dispersion coefficient is the function of magnetic field, electron density, and angle between wave vector and magnetic field. Next example is the propagation of two-dimensional linear waves on surface of shallow water, when dispersion coefficient is a function of depth. One more characteristic example is the propagation of the soliton-like internal gravity waves at heights of the ionosphere's S layer in regions with sharp gradients of the ionospheric parameters, including the regions of the fronts of solar heavy-night and a spot of solar eclipse. Now let's consider the second example. And first and third examples I will consider in my next talk. Consider an example of two-dimensional linear waves on surface of shallow water when in the GKP equation coefficients beta and gamma are the functions of depth. We solved this problem for initial condition in form of solitary pulse with periodic boundary conditions using the model of a bottom of type of step or a sharp brick of a bottom for positive step and or negative step. Here you can see our numerical results. In the first case, when negative step takes place directly under initial disturbance, we observe that perturbation caused by sharp jump of the dispersive parameter beta has a local character, i.e. is not propagate together with leading forward soliton. The asymptotes of separated soliton become oscillating, you can see. On a background of long wave fluctuations of a soliton tail, you can see also the wavy oscillations. Here, for the case of positive step is far ahead of initial disturbance, and you can see that soliton evolution at an initial stage practically doesn't differ qualitatively from its evolution at beta is constant. However, in further, its character is defined by presence of step because of the intensive generation of forward front on forward front of harmonics with great wave numbers kx. There is an appreciable changing of the solital structure, which can lead to overturning of the wave. In conclusion, we have discussed here some problems of the multidimensional solitons dynamics in complex dispersive media being described by the PK model, GPP and 3D less equations, taking into account the high order dispersive corrections and influence of dissipation of Gauss time. Namely, we have discussed the stability of two-dimensional and three-dimensional solitons, possible classes of stable and unstable two-dimensional and three-dimensional solutions, and asymptotic behavior of solutions. Also, we have discussed some of possible applications of the theory, such as propagation of the fastness of the sonic wave in magnetized plasma, nonlinear effects for three-dimensional affine solitons in the plasma, and the evolution of two-dimensional nonlinear waves on surface of fluids with variable dispersion. Other applications will be considered in my next talk today afternoon.
Yes, I have a couple of questions. So first of all, you begin with saying that this proof that extremes like minimum and maximum, they have absolute stable. They are absolutely stable, and therefore you are looking. Okay. So the question is: are these the only absolute stable points or not?
No. No. We have obtained the conditions for absolutely and locally.
Yes.
Depending on various of equation coefficients.
Okay, so it's not complete classification. It is just classification for the cases that you stated at the beginning. Yeah?
Yes.
With external. Okay.
Yes.
Okay. And the last slide, you are talking about applications, and you regard surface water waves. Just previous slide. One slide, yeah, conclusions. Yes, conclusions. Yeah. Yes, evolution of two-dimensional nonlinear waves on the surface with variable dispersion. How do you get variable dispersion? With bottom or how? What do you mean here?
Yes, dispersion coefficients beta and gamma are the functions of depth.
Yeah, I understand mathematics, but you're talking here about applications. So, how? What is the physical example of the situation when you have for this type of waves variable dispersion? That is the question.
There are many physical examples. For example, going tsunami waves to the coast.
So bottom, you mean variable dispersion? You mean just variable, for instance, variable bottom? So the values of h is variable.
In time and in space variable.
So dispersion function stays the same. It is just the changing of the value of parameter.
Yeah.
Okay. Okay, thank you.
Thank you. Thank you.